Step outside on a clear, dark night. Look up. What do you see? You see a beautiful velvet blackness scattered with a glittering dust of stars. For millennia, humanity has stared into that abyss with a profound sense of wonder. We saw patterns, we told stories, we charted the heavens. But for most of our history, those pinpricks of light were just that. Lights. We knew of the planets in our own cosmic backyard, our familiar celestial neighbors. But we could only dream about what might be orbiting those distant, lonely stars. We wondered, are they suns, just like our own? And if they are, do they have their own families of worlds? Do they have their own planets, silently spinning in the dark? That simple question has driven one of the most exciting journeys in modern science. It's a question that transforms the night sky from a static, two-dimensional canvas into a dynamic, three-dimensional universe of almost unimaginable depth. Each star becomes a potential campfire, a source of warmth and light for worlds we have yet to see. Today we are living in a golden age of discovery, an era where speculation is turning into fact. We are the first generation of humans to know, with scientific certainty, that our solar system is not unique. The universe, it turns out, is teeming with planets, billions upon billions of them. The implications of this are staggering. They force us to reconsider our place in the cosmos. The stars you see are not just distant fires, they are the lighthouses of other shores, other potential homes. Every single point of light is a clue, a destination waiting to be explored by our telescopes and our imagination. So, astronomers act like cosmic detectives, searching for subtle clues left as planets interact with their stars. One top method is the radial velocity method, also called the wobble method. Picture a star and planet in a gravitational dance. The star's gravity holds the planet in orbit. The planet's smaller gravity tugs back on the star. That tiny tug makes the star wobble slightly. It's minuscule, but measurable. When the star wobbles toward us, its light is blue shifted. When it wobbles away, the light is red shifted. This is the Doppler effect, like an ambulance siren changing pitch. By measuring those tiny rhythmic shifts over months or years, astronomers infer an unseen companion. They can estimate the planet's mass, they can estimate its distance from the star. It's an astonishingly precise technique. Another hugely productive method is the transit method. It's a game of cosmic shadows. Watch that distant searchlight again. If the moth flies between you and the light, you'll see a tiny dip in brightness. That's exactly what Kepler was built to detect. Kepler stares at a patch of sky, monitoring the brightness of hundreds of thousands of stars with extreme precision. If a planet's orbit is aligned, it will pass in front of its star from our view. That's called a transit. The telescope records a tiny repeating dip in brightness. That dimming is the shadow of a world. The dip's size tells us the planet's relative size. The time between dips tells us the planet's year. The transit method discovered the majority of exoplanets, growing our count from a few to thousands. It's a simple idea that revealed how common planets are. By patiently watching shadows, as the discoveries began to pour in, we realized that the universe is far more creative than our own solar system might suggest. We started to find planets of types we had never imagined. One of the first and most surprising discoveries was a class of planets known as hot Jupiters. These are gas giants, similar in size or even larger than our own Jupiter, but they orbit their stars at an incredibly close distance, much closer than Mercury orbits our sun. With orbital periods of just a few days, their surfaces are scorchingly hot, with temperatures reaching thousands of degrees. They are worlds of eternal, blistering daylight, a far cry from the cold, distant gas giants we know. Then we have the super-Earths. These are planets with a mass higher than Earth's but substantially below that of our smaller gas giants, Uranus and Neptune. They could be rocky worlds like ours, just scaled up, or they might be water worlds, planets completely covered by a deep global ocean. Our solar system, curiously, doesn't have a planet in this size range, yet they appear to be one of the most common types of planets in the galaxy. Let's talk about the numbers, because the numbers are simply mind-blowing. 51 Pegasi b, the first exoplanet around a sun-like star, confirmed in 1995. For decades the count grew slowly, one by one, then dedicated missions like Kepler changed everything. Trickle, torrent, flood. As of late 2025, over 5,500 confirmed exoplanets. Thousands more candidates waiting confirmation. These are just the ones our current tech can find, a tiny fraction of our galaxy. Kepler stared at a patch of sky so small you could cover it with your hand at arm's length. In that window it found thousands of worlds. From that data, astronomers made a staggering prediction. At least one planet for every star in the Milky Way. One planet for every single star. The Milky Way has an estimated 200 billion stars. Up to 400 billion stars. That implies hundreds of billions of planets in our galaxy alone. For every grain of sand on Earth's beaches, there are thousands of planets in our galaxy. And our galaxy is one of hundreds of billions, perhaps even trillions. The total number of planets is beyond comprehension. This is a fundamental shift in how we see the universe. Earth was once the only world we knew. We thought planets were rare jewels, but now we know planets are common. They form naturally with stars. Stars are parents, not lonely wanderers. Almost every star you see likely hosts its own family of planets. The universe is a theater with billions of stages. The story of planets is one of unimaginable abundance. With so many planets out there, the next logical question is inevitable. How many of them could be like Earth? How many could be habitable? To begin answering this, astronomers focus on the concept of the habitable zone. This is often called the Goldilocks zone because it describes the orbital region around a star where the temperature is just right, not too hot, not too cold. For liquid water to exist on a planet's surface, water is the one ingredient we know to be essential for life as we know it, so the search for liquid water is our primary guidepost in the search for life elsewhere. If a planet is too close to its star, any water would boil away. If it's too far, it would freeze into solid ice. The habitable zone itself is not a fixed location. It depends on the star. For a hot, bright star like Sirius, the habitable zone would be much farther out and wider. For a small, cool, dim star like a red dwarf such as Proxima Centauri, the star at the center of the TRAPPIST-1 system, the habitable zone is much closer in and narrower. A planet in the habitable zone of a red dwarf would have a year that lasts only a few of our days. The discovery of this immense planetary abundance brings us face to face with one of the most profound questions we can ask. Are we alone in the universe? For all of human history, this was a question for philosophy or religion. Today, it is a scientific question, one that we have a realistic chance of answering. Knowing that there are billions of potentially habitable worlds out there transforms the famous Drake equation, which attempts to estimate the number of active, communicative civilizations in our galaxy. The variable for the number of planets with the potential for life is no longer a wild guess. It's a number we now know is enormous. The search for life, or astrobiology, is now a major focus of space exploration. Future telescopes, like the James Webb Space Telescope and its successors, are not just designed to find more planets, they are designed to study their atmospheres. When a planet transits its star, a tiny fraction of the starlight passes through the planet's atmosphere on its way to us. By analyzing the spectrum of that light, we can look for the chemical fingerprints of certain gases, what we call biosignatures. We can look for the telltale signs of oxygen, methane, and water vapor, gases that, on Earth, are maintained by the processes of life. Finding such a biosignature would be one of the most significant discoveries in human history. It wouldn't necessarily mean finding intelligent spaceship-building aliens. It would more likely be the discovery of microbial life, a planetary-scale biosphere that is altering its own atmosphere. But even that would be world-changing. It would prove that the spark of life is not a unique miracle confined to Earth, but a natural cosmic phenomenon that can arise whenever the conditions are right. It would mean that the universe is not sterile and empty, but biologically active. It would mean that we are part of a cosmic community of life. This is the grand prize. Every new exoplanet discovery, every analysis of a distant atmosphere, is a step towards answering this ultimate question. We may be the only intelligent technological civilization in the galaxy, a lonely beacon of consciousness in a silent cosmos. That is one possibility. Or, we may be just one of many, part of a vast, interconnected galactic ecosystem of life that has been evolving for billions of years. We don't yet know the answer, but for the first time in our species' history, we have the tools and the knowledge to begin the search in earnest. The silence we've heard so far might just be because we've only just started to listen. We live in a remarkable moment. We are the generation that looked up at the stars and found them to be not just lights, but suns. We are the generation that confirmed the existence of thousands of new worlds, turning science fiction into scientific fact. The universe that we now know is grander, richer, and more populated with possibilities than we ever thought. The awe you feel when you look at the night sky is no longer just an appreciation of its beauty, but an understanding of its immense, hidden depth. You are looking at an ocean of stars, and that ocean is filled with islands, with continents, with worlds.